Hello everyone. Today we have the pleasure to have Virginia Ciriano from Quantum Motion. And just as a small introduction, Virginia did her bachelor degree and master's degree in Zaragoza, in the University of Zaragoza in Spain. And then he did a master's degree in quantum technologies in the University College London. And afterwards, a PhD in quantum motion, where she's working as a senior quantum engineer since 2019. And today she's going to talk about spin qubits in silicon quantum dots. So Virginia, the stage is yours whenever you want.
Hi, so this talk is going to be about spin qubits in silicon quantum dots. I will start saying how they work, how to make them, how you can operate on them, and then followed by what are the current challenges and what is quantum motion, that is where I work, doing in this respect. So just as a quick introduction, quantum computers take advantage of phenomena that are unique to the quantum realm, such as superposition and entanglement, and uses them to solve problems that are very difficult for a normal computer. These problems are, for example, factorization, which of big numbers into the prime factors. This is especially relevant in banks and in cryptography. Also, database searches, and as well in simulating quantum systems. So the best way to simulate a quantum system, which is a very difficult task for a normal computer, would be to use another quantum system, like a quantum computer. And this way you could simulate molecules, and with big applications on chemistry, drug discovery, etc. Okay, so the basic unit of a quantum computer, it's a quantum bit, qubit. And the wave function of a qubit is a quantum two-level system that has an excited state that we call 1 and a grounded state that it's 0. And a very convenient way to describe the wave function, it's a point in a sphere. So the north pole would be the excited state, the south pole the ground state. Theta will mark the probability of being in state 1 or state 0, and phi is the phase. So as I said, to make a qubit, we only need a quantum two-level system. But what makes a good qubit? So the first thing is that it has to be very well isolated from the environment. So any kind of interaction of anything like photons, whatever, with your qubit, it's going to make you lose information. So for example, if you are in the excited state, it can decay. So that would make you lose information in this polar angle, theta. And the time in which you lose that information is the relaxation time, or T1. You can also have the coherence, which is losing information in your phase. That time is called T2. Okay, so you need something that's very isolated from the environment, but at the same time, you want to interact with it whenever you want to apply a gate. So it's a bit tricky, very isolated, then you want to apply some stuff on it very fast, and it has to be a universal set of quantum gates. Normally, a quantum gate would be like make this qubit rotate around the sphere. And with a universal set, you can make any operation, any algorithm. Okay. You also need to be able to read in which state you are. So you have your qubits, you do a quantum algorithm, and at the end you want to measure. You want to measure fast, otherwise you would be losing your information, and with high fidelity. What else? Yeah, also to know that you are making the correct calculations, you also need to initialize in a pure state. And this might be the most difficult thing of all. You need to have a qubit that it's in a in a structure that is scalable. You want to have a lot of these isolated qubits that you can interact with them on demand. You can make interact between them, but you cannot lose their information. So everything has to be very well controlled and scalable at the same time. It's a bit tricky to get some quantum two-level system that fulfills all these conditions. So at the moment, there is several platforms. Here I have a few subsets. There is superconducting qubits, ion traps, Majorana, photonic, and spin qubit. And some of them have already achieved quantum supremacy, like for example, superconducting and photonic. But at the moment, it kind of looks like there is a lot of possibilities. We still don't know which one would be the winning horse of the race. And it kind of looks like before computers existed, like the computers that we know, there were other technologies, like for example, punching cards or making holes in some cards to make calculations, or having vacuum tube triodes that would act like switches, same as transistors. And the transistors were looking better because they use less energy and they have less heating. But it wasn't until the invention of the integrated circuit that transistors really explode. And this is what is key to make any kind of computer is that you can scale it up and make it bigger and have a lot of qubits or bits in it. So I'm here to sell you silicon. So why would you use silicon instead of the other ones? The first reason, and probably the most important, is that the structures in which the qubits are very similar to the transistors that are made in foundry. So potentially you can take advantage of 60 years of research in silicon transistors and these facilities where they have developed a very specific method to create very reproducible devices. But also silicon, the material, it's quite good as an environment, especially if you are working with spins. The first one is because so spins are very sensitive to magnetic noise. And because silicon, at least silicon-28, doesn't have, the nuclear spin is 0, it's completely doesn't have any magnetic noise. At the same time, electrons in silicon have a very weak spin orbit coupling. And this means that the electrical noise is not going to get converted into magnetic noise. That is the one that the spin sees. So you have a very quiet environment. And the third one, which is quite nice, is that recently it was demonstrated that silicon quantum dots can operate at 1.5 Kelvin. Why this is important? It's because most qubits work at millikelvin. This is very expensive to get to these temperatures. And also the amount of cooling power in that stage, it's very small. So if you put there any kind of circuits, they are going to overheat that area and it's going to be much hotter. But the 1.5 Kelvin is cheaper to achieve. And also you can put like multiplexers and FPGAs and stuff that wouldn't hit your fridge. Okay. Yeah, so how did you make a spin qubit? First, you need to trap an electron, and to do so, you would create an electrical quantum well, like a zero-dimensional quantum well. Why do you want to trap the electron? Is to avoid phonon noise, which is the main source of decoherence. Okay. So how do you make zero-dimensional well? First, you need to compact into 2 dimensions. And to do so, you have two options. The first one is to use a metal oxide semiconductor structure. So you have a silicon layer. You cannot see my thing. If you have a silicon layer here, and you apply some voltage to the metal, positive voltage, the electrons are going to get attracted to that metal. And they would create a two-dimensional gas. The other way to create a two-dimensional gas is to use the difference in the band structure between two materials. So you can put silicon in a sandwich with silicon germanium, and that would make you the same thing. That so this is in the deep axis, and the electrons would be like making like a crepe or like an omelette there. And now to make it, don't find my mouse, to make it a 0 dimension, you make gates on top of this crepe or omelette of electrons, and that's how you make 0 dimensional potential wells, which are called quantum dots. Okay, and because their dimensions are so small and they are at low temperatures, their energy levels are discretized. So when we apply a magnetic field, we can separate the energy level into the spin up and spin down by the Zeeman energy. Okay, so far we have our quantum two-level system, but how we interact with it. So the main way to interact with it, it's doing electron spin resonance. So with electron spin resonance, you apply a AC magnetic field at the same frequency as your Zeeman energy in a perpendicular direction to the one you are applying to create the Zeeman energy difference. And that's going to make your spin rotate. So you can change it from, for example, a spin up to a spin down, or depending on how long you are applying this oscillating magnetic field, it can rotate for more time or for less time. I mean, it can rotate more or less. Okay. So how do you apply this oscillating magnetic field in near this quantum dot? You can have this kind of antenna, and you apply an oscillating current. Oscillating current in the antenna produces an oscillating magnetic field. So you can measure the state of the qubit after, so you rotate it for a bit and then you measure and do the same for more and more and more time. You start to get Rabi oscillations. So the measure, the 1 qubit fidelity is above 99.9% of fidelity. And this number, it's important because, well, it's a bit long to explain, but in quantum, you would like to be able to correct your operations so they don't have failures. And the limit for be able to have quantum error correction, at least using an algorithm that is called surface code, is 99.9. So if the fidelity of your operations is above 99.9, it means that you would have an error-free quantum computer. Okay, so another way of creating this oscillating magnetic field near your quantum dot would be to put micromagnets near your quantum dot. Now, your macromagnets, what they do is that they modified the magnitude of your magnetic field in the space. So instead of having to apply directly an oscillating magnetic field, you would apply an oscillating voltage that makes the electron moves back and forward, and that changes their magnetic field. So effectively, you are applying an oscillating magnetic field. The advantage of using these micromagnets, which is called a electrical dipole spin resonance, is that the operations are much faster. And that's usually, it's better to have fast operations so you won't lose your information while you are doing one qubit operation. Okay, so far we know that these qubits can be made with a spin up and a spin down of an electron. We can do 1 qubit gates on this electron by applying oscillating magnetic field or electric field. And now I'm going to talk about how to make a 2 qubit gates. So to make a quantum computer, you need at least 1 qubit gates to rotate the qubit in 2 different axes, but you also need to have 2 qubit gates. And to make 2 qubit gates, there are different ways to make them. Today I'm only going to explain one kind, but there are basically two interactions that are important. The first one is the spin-to-spin exchange, and the other one is the G-factor difference. So imagine that you have 2 quantum dots that are quite close to each other, and you have 1 electron, 1 in each dot. Now, because of the material difference or some strain, normally the G-factor is slightly different in one quantum dot than in the other. And that means that if we see this 4 energy level system, the energy that takes to go for the for the blue dot from spin down to spin up, it's smaller than the energy that takes for the red spin to go for spin down to spin up. Okay. Now, when we try to place those electrons to closer, and we could do that by, well, remember that we have 2 quantum dots that were already close, but there wasn't any tunnel coupling between them. We can pull the wave functions together either by decreasing the tunneling barrier between the dots or by trying to make one of the electrons go inside the other dot. So when the electrons become delocalized and the wave functions are together, we have the electrons create the bonding and anti-bonding states. So the 4 states that we had before, now their energies are slightly different. And this is called the exchange, spin-spin exchange or exchange interaction. Okay, so what the combination of the difference in G-factor and the exchange interaction has done to us is that now the energy between having the blue dot with a spin up or spin down, which is the pink arrows, it's different depending on whether the red electron has a spin up or a spin down. So we can take advantage of this situation. This situation was different Zeeman energies for one of the dots depending on the state of the other electron. Wait, I'm going to pass this. And we can use this to make a C0 gate. What is a C0 gate? Well, I can explain it by the initial state and the final state after applying this gate. A C0 gate is a 2 qubit gate. So if you have both of your spins down, you will finish with both of your spin down. If you have the red one down and the blue one up, then you finish with the same. But things change when you have your red electron up and the blue electron down, because that makes the blue electron change. And the same happens when you have it. I made a mistake here, but basically what the CNOT gate does is that if you have your red electron, which would be the control, down, nothing changes in the blue. But if you have it up, the blue is gonna flip. So if you have it down, goes up. If you have it up, goes down. This is a CNOT gate. And to do a CNOT gate, we're also going to use something else. That is that if we put the spin or the qubit in a superposition between the up state and the down state, it's going to rotate around the sphere. We remember the sphere was the state in which it is, the spin. And the speed that it rotates, it depends on the energy between the spin up and the spin down. Okay, so how would we apply this CNOT operation? First, we are here where we just have our 4 levels, and we apply an X gate, which means to pass the blue electron from the spin up here to a superposition of the spin up and the spin down. Now we're going to put the electrons together, which would turn on the exchange interaction. So the spin is going to rotate around the sphere, but it will rotate around the sphere at different speeds, depending on whether the red electron has a spin down, or it has a spin up, or a spin down. Okay, so we have seen that they have rotated at different speeds, and now when we applied again another X gate, one of the blue electron has finished with the spin down, whereas in this situation it has finished with the spin up. Okay, so far we have charge speed conversion, we have single qubit gates, 2 qubit gates, and we're just missing how to read our dot. We can read it in 2 different ways, either using one dot or using 2. Okay, so I will start with the first one. To read a single spin, it's very difficult. So what normally people do is, instead of reading the spin directly, it converts the spin state into some kind of charge tunneling. And instead of measuring the spin, we're measuring the electron moving to a different place. So, for example, we're going to place our qubit close to a reservoir that is tunnel coupled to. So if the qubit has a spin up, it will leave the dot and then come back. And we can see that in a charge detector. On the other way, if we had a spin down, the electron will keep inside the qubit and we won't see any change in our signal. So this way we can measure the time that it took for the electron to tunnel out and then back in. Okay, we can do a similar thing, but instead of measuring one single electron, we're measuring 2 together. And to do so, we have 2 electrons, each of them in a different quantum dot. So if the electrons are in different spin states, they are in the form a singlet, then this electron can tunnel to the other dot and they can be together. Whereas if they are in the same spin state, it cannot tunnel there because of Pauli spin blockade. So in this way, we will see that the signal is constant in light blue if we had a triplet, unless if the triplet decays. And the signal changes because we have had a tunneling event if we had a singlet. So in the current state of silicon, we have very good decoherent times and relaxation times above what superconducting qubits do. And we also have all single qubit, 2 qubit gates, readout, and initialization above the surface error threshold, which is 99%. This is very good. But most of these experiments are done in quantum dots that are fabricated in academic clean rooms. And what would be the goal would be to move from this academic way of building stuff and be able to get all the facilities and foundries that already exist and try to make the transistors using foundry fabricated devices. Yeah, so the main challenge right now for the community is scaling from this demonstration of 1 qubit on 2 qubit dots and try to do the same thing, but for a lot of qubits. And this is exactly the goal of quantum motion, which is where I work. And the goal is demonstrate that the scalable quantum circuits can be built using industrial silicon technology. So just a bit of an overview of what quantum motion is. It's a fast-growing startup in the UK. We have our lab with many dilution fridges in London, but we also have a branch in Oxford, and it covers 3 different things. On one part, it would be the integrated circuits team that designs and tests transistors that can be fabricated in foundries and check if they are quantum dots at low temperatures. We also work doing cryogenic classic electronics, so all this circuitry that you need inside the fridge to operate on the qubits and amplifying your signals, etc., etc. We're also trying to scale up silicon quantum dots in any way we can. And there is also a part that does hardware-aware quantum algorithms. So far, I think we have more, but at the point that this was written was 18 researchers, and there are also a bunch of PhD students. I think I already said mostly what's in this slide, but just to say that we have recently named to be top startups worth watching in 2021, and we have many investors. Between them there is Bosch and Oxford Science Innovation, Octopus Ventures, etc. So now that you know what is quantum motion, I want to tell you how you can scale up these silicon qubits. Yeah, so there are different paths and all of them combined together. The first one is trying to build uniform quantum dots. So as I said, most of the demonstrations are in academic foundries, and it would be nice to get what is done in already developed foundries and modifying the minimum, make it work as spin qubits. And in fact, this is not something that only quantum motion is doing. Other groups are doing it as well. They have taken up the challenge. And some people have gone even further and tried to implement in the same chip, not only the qubits, but also other circuits and stuff. Okay, so one is making uniform quantum dots. The next thing would be minimize all the structures that you need around your qubit. In terms of 1 qubit gates, passing from having one antenna close to every quantum dot to have global control. And in terms of 2-qubit gates, could be, so as I said, to do 2-qubit gates, you need to put two electrons quite close together. So you cannot do something that is not nearest neighbors. And people have thought about doing modular architectures where you have your qubits, then some circuits that you need close, and then qubits again in modules. And in that front, recently, Sophia, which is one of my coworkers, have achieved to do charge sensing of remote quantum dots at a distance of 510 nanometers, which doesn't seem much, but is a lot when you compare it with this would be 20 or 10 or maybe 5 nanometers if there wasn't this elongated dot between them. Okay. Yeah, something that we do a lot in quantum motion is READOUT. And to be fair, I think I overextend my time in this seminar because I still have a lot of slides explaining how the READOUT is. So do you want if I skip that? Or I'm not sure.
How much do you think you will overextend?
I don't know, maybe it's 15 minutes. Maybe I think I can, it's very, there is no need. There is no need to explain it.
Okay, up to you. If you find it important, just extend a bit.
I don't think it's that important. Okay, so something that I didn't mention, before I just said that to read out an spin state, you need a charge sensor, but I haven't said anything about what is a charge sensor or how would you do a charge sensor. And the most common way is to use a quantum dot. There are different ways to making this sensor, and recently we've been trying to specialize into making this charge sensor as small as possible. So you could potentially integrate a lot of them together without being annoying for the qubits interaction. So remember that the qubits need to be quite close to interact between each other, so you cannot have big sensors close to them. Okay. Okay, so what we did is we collaborated in a European project, and we have this nanowire. It works as a FinFET, which is a transistor, and it has two gates. If we see a transversal view, we can see that one quantum dot is formed under each of the gates. So we used one of the gates as a sensor and the other one as a qubit. And we were able to measure single shot traces, both in the both ways that I've described before. So in the left, there is the single spin measurement, and on the right, the parity measurements. And what was nice is that we reported very high fidelities in a very short time, so 99.2% in 5 microseconds. If we compared with what other people have been doing, they have around the same fidelities or lower, but either lower or but shorter, or higher fidelity but longer time. If you want to know, the SET, it's bigger than the SEB, and we are working with SEBs, which are smaller and better for scalability. Okay, so since we were able to measure the spin, we were also able to measure how long the spin was taking to decay, so our T1 or relaxation time. And the relaxation time changes depending on how much is your Zeeman energy, but we actually beat the record and we measured the longest spin relaxation time using a CMOS transistor, which is 9 seconds at 1 Tesla. Okay, so far we are tackling uniform quantum dots, minimize the structures, but there is also the problem of wiring. So this is an image of the Google quantum processor, but we can see that it has a lot of cables, and it's because currently in all the qubit implementation, each qubit is wired one by one, and this becomes a bottleneck in terms of wiring. So instead of having a lot of wires that come from room temperature to the qubits, we would like to have something in the middle that makes the connections a bit. Then in this part, which would look like a DRAM or a multiplexer, and then expand them. Okay, so far we were able to have the first demonstration of time domain multiplexing, which means that we were measuring through this RF line, and we were able to decide which sensor we wanted to sense. So we could close this transistor, so close that switch and measure only this quantum dot here, or we could do the opposite one, like switch this off and be able to read that one. And recently we have expanded on that work, and we've been able to measure 1024 quantum dots very fast in 12 minutes by using this thing in which you have few lines that go to a multiplexer, which is something that takes few lines and convert it into a lot, and then measure a lot of quantum dots. Okay, so in summary, just wanted to tell you that silicon has made very big progress over the past few years. It has very good fidelities for 1 qubit gate, 2 qubit gates, readout, and there are demonstration of up to 6 qubit processor. And in the path of continuing scaling up, the industrial fabrication of quantum dots might be an important factor, and that right now we're putting together the different ingredients to scale up silicon quantum dots. Okay, so if you liked what you've heard and you would like to join us, we have open positions for we have for a senior quantum engineer, which is more or less what I do, or for IC design engineers. So you can contact Quantum Motion, and thank you for listening.
Thank you very much. It was very nice. I especially enjoyed the introduction part. It was
very clear.
Yeah, very clear for every person. Yeah, so we can start by one question that was in the chat by like almost from the beginning. I think you've partially answered it throughout the talk, but maybe yeah, you can deep in a bit more. It says, it's by Reza, the question, and it says, hi, how do you measure single qubit gate fidelity, considering you have error in initialization, readout gate itself? I think it comes to that plot you showed about the 99.9% fidelity.
Okay.
It was around that time the question was made.
I think you cannot really separate it from the error you have in readout, because that's just going to be there. You could, and the same with initialization, it would be very difficult. I haven't done it, so I'm not sure how would you do it, but one way that you could simulate how much is your decoherent time, because you are going to see your Rabi oscillations decay, and you can simulate, knowing that my decoherence time is that, I can know how much my gate fidelity is, knowing that I have to apply my rotation for, I don't know, 20 nanoseconds. But if you are going to measure it experimentally, you can measure the fidelity in the readout. And that way you can say this percentage comes from the readout and this percentage comes from the qubit dot as an accumulation of error. But it's a bit difficult.
Yeah, I think it was answered. But Reza, if you have any further question, just unmute yourself.
Okay.
Yeah, Reza says thumbs up.
Okay.
Yeah, anyone else, if you have any other question, you can just unmute yourself and ask it, or also type it in the chat and we read it for you.
Now that we are in this very same slide, you commented something about the surface code and the relation to having a fidelity above 99.9%. Can you repeat that, because I got a bit lost?
Okay. So just, you know, I'm not an expert on this part, but
okay. Me neither.
So quantum error correction, it means that you are constantly measuring your qubits over and over. You are doing a special kind of measurement that you don't lose information. But in order for this this way of avoiding or correcting your errors, you need to have a minimum amount of good stuff. So if your gates are horrible and you're doing horribly and your measurement is horrible, it doesn't matter if you have you are correcting anything, because you are correcting badly, and it's just not improving anything. So the minimum fidelity, which is the percentage of times that you have correctly achieved what you wanted, it has to be 99.9.
I see. Thank you.
Okay, there's another one in the chat by Julio. What was the name of the other way of implementing a magnetic field with higher rates?
Julio, I think you mean in the slides that we are right now. I think, okay. So one is called electron spin resonance, and that's applying an oscillating magnetic field. The other one, the one you're asking for, is electron dipole spin resonance. Electron dipole or dipole. Not sure how to pronounce it.
Yeah, I think Julio is satisfied by that answer. I had also a question which is a bit broad, and you already talked about it as well, which is, so you commented that now most of these things are made in like academic clean rooms, and that the idea would be to make it, yeah, that I really didn't understand. Like, how are you trying to make these things done in a foundry? Like, you want to make kind of an instruction set that you would give to the people in the foundry, and they would make it with the technology they already have, or would they have to change their machines, or how would that process be? And also, how long do you think that could take, like, until qubits are made in that way?
Okay. So sorry. Yeah. So when you send it to the foundry, sorry, let me structure my thoughts. One second.
Yeah, so I didn't make a very concrete question. It was maybe my fault. I just talked a lot, and but yeah, my question was like, those foundries, you don't own them, right? It's people you send the design or whatever. No?
Okay, I got it. So in academic foundries, you have complete freedom of what you want to do, which material you want to use, and most of the stuff that is bad for qubits, it's charge defects. So when you can design which material you want to use, you can be very like precise of, oh, I want to use this material because it's so much better. But in the foundries, they are quite strict about, we are only going to use this and this and that because all of our machines are doing for this and this and that. And they are very like strict on not changing what they're doing because it takes millions to optimize what they're doing. Yes, so how long it would take? If you send them a recipe, I don't think they would do it unless it's a recipe that it's similar to what they are doing recently. So before we were working with Leti, which is a foundry in France that when a normal foundry wants to do an experiment or experiment with a new technology, they go to that foundry and they try new stuff. But now we're working with normal foundries, which are more strict. I think, I mean, we're getting quantum dots from them, and I don't think it would get that far until we have a qubit. I give it to 1 year, 2 max. And actually, I think people in the Netherlands, which are working with Intel and Intel itself, so the people in the Netherlands working with Intel, I think they have 1 qubit gates. So I don't think it's that far. It's really not.
Nice, very optimistic. Thank you.
Okay. I don't know if we have any question in the chat. No? Okay. Okay. So if there is any other question, I think we can finish here. Okay. So thank you very much, Virginia, for the talk. It was really interesting and very pedagogical. So thank you very much. And thank you very much for attending.
Goodbye. Yeah, thank you. Thank you very much.
Thank you. Thank you for listening. Bye.